Starting in on our next chapter, chapter 17, on Tuesday of next week, what we'll do is we'll kind of rewind back and do a review session before the exam, and then we have our exam on Thursday, all right? To be clear, the exam will not contain this chapter 17 alcohols material, okay? This is just kind of to make sure we're staying on track here. Was that your question, Anthony?
Yeah.
Okay. All right, so now we're going to move on to chapter 17, alcohols. We've already seen alcohols a lot. We've certainly worked with them a lot in the lab. We haven't ever kind of like talked about them as a functional group though. All right, so what we're gonna do is focus, kind of do a deep dive on alcohols in this particular chapter. All right, so our alcohol, I think we know, but just to remind ourselves, is when we have this hydrocarbon chain and this hydroxyl group. All right, to be clear, the functional group here we would call this an alcohol. This bond is what we call the hydroxyl bond. So that's why you hear both of those terms kind of thrown around when we're talking about alcohols. All right, similar to how like a ketone has a carbonyl group, an alcohol has a hydroxyl group, right? That's specifically that OH bond. All right. What do we know about these OH bonds? Even like rewinding all the way back to Chem 1A, Chem 1B, talking about intermolecular forces. We have our weak dispersion forces, we have our dipole-dipole interactions, and then we have those special hydrogen bonding interactions. All right. This group right here is capable of what? Our hydroxyl group. Hydrogen bonding, right? And that was that strongest polar force that you can have. So our alcohols are characterized by this polar functional group here. All right, but if you remember all the way back to the beginning of last semester, you did a bunch of solubility tests on alcohols, and you found that like as soon as you hit 4 carbons, your alcohols are no longer soluble in water, or rather butanol is like partially soluble, and anything bigger than that is insoluble in water. So why would that be? What's going on the back half of this molecule here?
It's non-polar.
All right, this one only has those dispersion forces. So this would be non-polar. All right. So bottom line is we think of alcohols as being a polar functional group because that functional group, that hydroxyl group, is indeed polar, but kind of devil's in the details with how polar the molecule is as a whole because it's also got this non-polar end, that hydrocarbon. Cool. All right, and we're going to sort of punt on talking about physical properties of alcohols until we get to the next chapter where we introduce a few more functional groups, and then we can compare and contrast this group of functional groups and talk about their physical properties. So right now we're just going to kind of dive into reactions, and we're going to focus first on ways that we prepare alcohols. Hold on a second. Okay. I got a little paranoid that I wasn't recording. Okay, so preparation of alcohols. The first place we're going to start is actually reviewing reactions that we covered last semester. These are our hydration of alkenes. All right, so what we learned last semester when we were talking about how alkenes are these various hydration reactions that add a water molecule. They add a hydrogen to one side and an OH group, that hydroxyl group, to the other side of our alkene. All right, so our hydration of alkene reactions means that we're going to take a carbon-carbon double bond. Okay, we're going to learn a few different reagents to do it, so I'm just going to say hydration for right now, or we're going to add this water molecule. Okay, and again, that means that the hydrogen goes on one side and the hydroxyl group on the other. Okay, what type of reaction is a hydration reaction? Are we substituting, eliminating, adding? So this would be an addition reaction. Yeah, we're adding to either side of that double bond. So this is our hydration of alkenes. All right. And we'll sort of talk about each one of these individually, but let's just kind of make a little master list of our reactions that are considered hydration of alkenes. The first one is what we just simply called an acid-catalyzed hydration. Okay, this uses dilute sulfuric acid, so H2SO4 and water. All right, we also had a oxymercuration reaction. This used that mercury acetate and water. Hold on. Okay. I didn't want to get the second step mixed up on these two. The second step here is sodium borohydride, which we'll actually talk a little bit about this class as well. And lastly, what was called a hydroboronation reaction. All right. This is where you use that borane, BH3. Sometimes the solvent's specified in THF. Followed by hydrogen peroxide and water. All right, so these are our reagents here for each of these three different hydration reactions. All of these will add a water molecule to your alkene. What's up?
You said water. Did you mean sodium hydroxide?
No, all these reactions will add a water molecule to the what?
For the second step, you said adding peroxide and water.
Okay, then yes, I did mean so. This is correct. It is sodium hydroxide. I got ahead of myself in my thoughts. Yes, adding sodium, hydrogen peroxide, and sodium hydroxide. These are three different methods to add a water molecule to an alkene. That was how that should have come out. Okay, so all right, so let's take a kind of deep dive in each of them. We'll note that this one right here is kind of special in that we know our mechanism for this acid-catalyzed hydration ones. The other ones were left as a little bit more of a mystery. We didn't actually look at our electron pushing arrows for those, but we're going to start with this acid-catalyzed hydration reaction. Okay, so let's take an alkene. All right, since this reaction uses dilute sulfuric acid, We're not going to use sulfuric acid in like explicitly that Lewis structure in our mechanism here, because as soon as a sulfuric acid is added to water, it will react with water to produce hydronium ions, right? So we're going to use hydronium ions in our mechanism here. All right. And maybe we should just note why we're using hydronium ions instead of the molecule sulfuric acid. All right, this is created when H2SO4 and H2O are combined. All right, kind of an important distinction between when we say we're using concentrated sulfuric acid versus dilute sulfuric acid. This is dilute sulfuric acid here, so really our acid molecule are our hydronium ions. Hydronium is also an acid, right? So what role do our acids play in our chemical reactions? Electrophiles or nucleophiles? Electrophiles. All right, so this was one of the very first things that we kind of went over at the beginning of the semester when we were doing our review. I will tell you, you can expect me to ask you those questions on the exam from that review week, this classifying of electrophiles and nucleophiles. That's just one of the most important things that we should take away. As we're moving forward, that's what's going to help us start to predict these reactions. I will say these next two units are much more reaction mechanism heavy than the previous unit that we just did. I think we maybe looked at 2 of them in the previous unit. Going forward, we're going to have a lot of reaction mechanisms. And one of the ways that we're going to keep them straight is to be able to look at stuff and say, all right, I know this thing's going to be my nucleophile and this thing's going to be my electrophile, okay? So anyways, we reviewed it at the beginning. Like I said, you could just expect me to ask it on the exam, okay? So if this thing's my electrophile, my kind of gave it away. My alkene here is my nucleophile, and specifically, what's my nucleophilic site? The pi bond. All right. What's my electrophilic site in an acid? That donatable hydrogen, yep. And so what do nucleophiles do to electrophiles? They attack. And so our first step here is we're going to have that acidic hydrogen get attacked by our alkene. All right, we're going to be good and show that this first step here is reversible. Actually, I think stepwise, I'm going to put it down here. Okay, is this a bond breaking or bond formation or both arrow? So this is bond breaking, so this just simply kicks off that leaving group, that water molecule. All right, and then this one is what? Bond breaking, bond formation, or both? Both, right? I'm breaking a carbon-carbon bond, and I'm creating a new carbon-hydrogen bond. All right, and so I have 2 options. Which carbon is going to hold on to that pair of electrons? Over here or over here? Which one of these is going to be my correct placement of my double bond? Let's actually, before we do that, let's go ahead. Something's missing from this structure here. The carbocation, right? One of those carbons got that pair of electrons taken away from it, so we have this carbocation intermediate. And which one of these is actually going to form in this reaction? The one on the left or the one on the right? The one on the left. And why was that? More stable because it's more substituted. Absolutely. All right, so I'm just going to get rid of this one here. So we have our carbocation intermediate, and that's kind of the most important things to remember about this reaction here. We're going to note especially we have a carbocation intermediate. All right, so then let's look carefully at what we have in our reaction mixture now. Now we have a carbocation and a water molecule. Our carbocation is going to play the role of what? Nucleophile or electrophile? electrophile with that positive charge. So then water is going to be my nucleophile. And specifically, what's my nucleophilic site on this water molecule? The oxygen. All right, so let's have our nucleophile attack. All right, I'm going to give you a second. Draw this intermediate here. Make sure you got your formal charges and lone pairs and all that jazz. All right, so I have my oxygen, but it's still got those two hydrogens bonded to it. Now I need to complete its octet by giving it one lone pair. And what am I missing? Positive formal charge. Okay, so we're almost there. We're almost at an alcohol. We've just got one extra proton on there. So what we need is we need some base to come along and remove that proton. All right? Some base is going to come along and remove that proton. But what is the base going to be here in this reaction mixture? Okay, real quick before we answer, let's remind ourselves here that we talked about these different conditions with regard to our reaction mechanisms. And this one, being an acid catalyzed reaction, means that we're under acidic conditions. So this is an acidic conditions mechanism. If we have a mechanism under acidic conditions, all right, our rule is that we can't have any intermediates, anything in there that is a strong base. So under acidic conditions, we have no strong bases. All right, so what I can't use would be something like a hydroxide ion. This would not be able to survive under acidic conditions here, so this is definitely not what my base is going to be. All right? In fact, under these acidic conditions, I'm going to need to use not a strong base, but I'm going to use a weak base. All right? And so what weak base do I have floating around in this solution? Water. Awesome. Okay. So what's going to play the role of our base? One of those water molecules. And what you'll notice is that this allows us to reform that acid catalyst, right? Catalysts aren't consumed in our reaction, so we spit out another hydronium ion. Cool. All right, and what we said here is because this alcohol group goes on that more substituted carbon, we had a fancy Russian name for this type of reaction here where you add to that more substituted carbon. This was a Markovnikov addition. All right, but the pain in the butt thing about this reaction, because it has that carbocation intermediate, what are we going to warn ourselves about? Those shifts, right? We got to watch out for shifts. Okay? Cool. Our oxymercuration reaction. Okay, this is one that we don't have a mechanism for, so we're just going to kind of note some key things here. All right, again, this is when you take that mercury acetate and water. Follow that up with that sodium borohydride. Oxymercuration is also a Markovnikov addition. All right, but for this one, we had no shifts to worry about. All right, and then the last one, our hydroboronation. Again, we're not going to look at a mechanism for this one. So we're just going to note our reagents here. Again, hydroboronation uses borane, BH3. All right, and then we have that second step with hydrogen peroxide and sodium hydroxide. And the difference between our hydroboronation and these previous reactions is that they were both Markovnikov, and this one is what we call anti-Markovnikov, where that hydroxyl group is added to the less substituted carbon. Okay. This is what we would call our regioselectivity. This also had that stereoselectivity that we had to worry about, where you would get a stereospecific product because it was a syn addition. All right, so let's just make a little summary here of these various hydration reactions. All right, we're going to make a little wheel. I'm going to put this alkene down. And we're going to do both, or rather all three, our dilute sulfuric, our oxymercuration, and our hydroboronation. All right, so take a second and fill out this little wheel here. What are our expected products given this same alkene for each one of these reactions? All right, so I'm going to color this carbon in blue, and I'm going to color this carbon in red. Let's start with our oxymercuration reaction. If I take that alkene and do an oxymercuration reaction, where am I going to add that hydroxyl group? To the red carbon or the blue carbon? The blue, the more substituted carbon will get that hydroxyl group. The other one gets a hydrogen. I'm just going to leave that as implied. All right, what about my hydroboronation reaction? If I do that, red carbon or the blue carbon? Now it's going to be that less substituted carbon gets the hydroxyl group. All right, and then finally, when I do my dilute sulfuric acid, am I going to add it to the red or the blue carbon? All right, cool, yeah, trick question. This is a good example of when that carbocation intermediate comes into play, and I would get a hydride shift, adding it to that more substituted green carbon here. All right, and let's just show this real quick because it's been a while since we've hydride shifts. All right, so first of all, we would take our alkene, and we know that this is going to be converted. I'm going to sort of be lazy here and just skip the full mechanism and the arrows and all that jazz, and just show our intermediate, our carbocation intermediate. All right, but how do we know that this thing is going to undergo a hydride shift? Like, what was it about this molecule that made it obvious to us that that hydride shift was going to occur? There's a more substituted carbon right next door, right? So the thing that pointed it out to us was the fact that this is secondary, and right next door is a more substituted carbon. All right, so let's just point out, when do we have to worry about these hydride shifts? When our next door neighboring carbon is more substituted. All right, so just to kind of finish this off mechanism-wise, we have a hydrogen. That hydrogen's going to jump over to that secondary carbon there, which is how we get our carbocation on that tertiary carbon. Cool. And that's why the water then ends up attacking that particular site, giving us this product here. So I kind of strategically chose this alkene to help illustrate the differences between these three reactions. All right. Again, we can just kind of summarize. This one was Markovnikov. And we said we got to watch out for shifts. This one was also Markovnikov, but we didn't have to watch out for shifts. And this one was anti-Markovnikov. All right. We also noted that this one was that syn addition. I'm going to kind of punt on that stereochemistry. We talked a lot about it last semester. It was kind of a big pain in the butt. We got enough going on in this chapter to not really have to worry about the stereospecificity of this reaction. You kind of would have to have a very specific alkene anyway for it to matter, and we'll just dodge those examples. All right? Cool. So one of our methods of preparing alcohols is this set of reactions that we learned last semester, these hydration reactions. All right, we can hydrate an alkene to form an alcohol. Cool. All right, so the other thing that we're going to learn, the next set of reactions that we're going to learn, this would be a way to create alkenes or create alcohols. All right, these are our oxidation reduction reactions. We talked a little bit about oxidation and reduction last chapter. All right. Again, talked about it in Chem 1B, and it was a big pain in the butt. You had to go in and assign oxidation numbers to figure out who was gaining or losing electrons. That's because that particular context of talking about redox reactions, we were mostly talking about like transition metals and stuff like that. So we always had these metals that were involved. In organic chemistry, oxidation and reduction are a little bit more straightforward because we're talking about so few elements on the periodic table, right? We're much more confined to our nonmetals, specifically having carbons and hydrogens. All right, so oxidation is when we've created more oxygen bonds, and reduction is when we have fewer carbon-oxygen bonds and more hydrogen bonds. Let's say carbon-oxygen and carbon-hydrogen bonds. Okay. And we're going to talk about these alcohols and their oxidation reduction reactions. All right. Importantly, we're also going to need to introduce this classification system that we have for alcohols. All right. So this alcohol here we would call a primary alcohol. Use that little 1 symbol. And that's because that hydroxyl group is bonded to a primary carbon, a carbon that has only one other carbon neighbor. All right, we can also move that hydroxyl group over to that second carbon. This is what we would call a secondary alcohol. Because that hydroxyl group is bonded to a carbon that has two other carbon neighbors. All right. Or if that carbon had 3 other carbon neighbors, as in this example here, this would be a tertiary alcohol. All right, and these are going to undergo oxidation reduction reactions a little bit differently, so we're going to break them up into these 3 categories here. All right, we'll talk about our oxidation agents here in a second. So for right now, for oxidation, we're just going to use this O in parentheses, or in brackets rather, just meaning oxidation. All right, so if we're going to oxidize this molecule, oxidize that carbon, we're going to create an additional carbon-oxygen bond, all right, or what we would call a carbonyl bond, carbon-oxygen double bond, which means that we've converted that primary alcohol into what? What functional group are we looking at here? An aldehyde. All right, but aldehydes, we could keep going here. We could continue to oxidize that carbon even more, giving it its maximum number of carbon-oxygen bonds. All right, replacing that last hydrogen with an oxygen, creating what functional group? Carboxylic acid. All right, so primary alcohols can be oxidized to aldehydes, which can be further oxidized to carboxylic acids. All right, and then reduction is just going the exact opposite way. So we could reduce a carboxylic acid into an aldehyde. So for reduction, I'm going to put R brackets. And we can reduce an aldehyde into an alcohol. All right, so let's play this same game here. But now we're going to talk about secondary alcohols. And just like we oxidized our primary alcohol to an aldehyde, what do you think we're going to do when we oxidize this secondary alcohol? What am I going to draw differently here? Another carbonyl bond. So we're going to turn that carbon-oxygen single bond into a carbon-oxygen double bond. All right, but we don't call these aldehydes. When they're in the middle of the molecule, we call them what? Ketones. All right, but if I tried to take this ketone and further oxidize it, I couldn't do that without breaking any carbon-carbon bonds, which isn't going to happen in these methods here. So a ketone cannot be further oxidized. We're stuck here. All right, and then by that same logic, if we do the reverse, we reduce a ketone, we would create a secondary alcohol. All right, so again, these are methods, specifically the reduction direction here is a method that we can use to create alcohols from ketones, aldehydes, or carboxylic acids. All right, and then lastly, if we take a tertiary alcohol and we try to oxidize it, can we create any more carbon-oxygen bonds? No. So again, we're stuck. Tertiary alcohols just cannot be oxidized at all. Cool. All right, so now I'm going to introduce you to our oxidation reduction reagents. Whoops. I guess we'll start with our oxidation reagents first. And what we're going to do is we're going to throw these oxidation reagents into two buckets. What we call our strong oxidizers, and then what we call our weak oxidizers. We're going to have two categories for these oxidation agents. All right. Our strong oxidizers are those oxidizers that we were introduced to last chapter. We have our sodium dichromate in that dilute sulfuric acid. All right. We also had that potassium permanganate and heat. All right, but our weak oxidizers are going to be new. All right, and they all have these acronyms. So the two weak oxidizers that we're going to be introduced to is PCC. And the other one is DMP. All right. These are, this one's Des-Martin periodine, and I don't really remember exactly what this one stands for, if I'm going to be dead honest with you. I know the middle C does stand for chromium, but they basically are these oxidation agents where somebody took something that was known to be a good oxidation agent and added a bunch of crap to it to make it a little bit weaker. All right, so why would they want to do that? So these are a little bit fancier design molecules. They're certainly a little bit more expensive as well. So then why would we want to use a weak oxidizer versus a strong oxidizer? All right, going back up to our little chart here, if we were to take a primary alcohol and use a strong oxidizer on it, it would oxidize that primary alcohol all the way to a carboxylic acid. All right, that's our strong oxidizer. You can't get it to stop at that aldehyde step there. All right, it will blow past that aldehyde and just fully oxidize that carbon to a carboxylic acid. And in fact, if we started with an aldehyde, we could use that strong oxidizer to create a carboxylic acid. But the bottom line is, if you're using a strong oxidizer, you're always going to end at that carboxylic acid. So what if I wanted to create an aldehyde? That's when I would have to use instead my weak oxidizer. Right? So our weak oxidizer, the reason that they created these things is because they help us stop at that aldehyde step. With a secondary alcohol, I can't oxidize any further than this ketone. So regardless of whether I used my strong oxidizer or my weak oxidizer, I would always end up in the same place. And with the tertiary alcohol, we can't do it anyway, so we're not worried about it. All right? So here's our big difference between our strong oxidizers and our weak oxidizers. They do the same thing to a secondary alcohol, but importantly, if we started with a primary alcohol, we would get a different product for our weak oxidizer than for our strong oxidizer. All right? Likewise, we got similar categories. I didn't leave myself enough room. We got similar categories for our reduction reagents. All right, we're again going to throw these into these two buckets, strong and weak. Okay, our strong oxidizer is lithium aluminum hydride. All right, this stands for lithium aluminum hydride. Actually, I'm going to be good here. We always have this second follow-up step. This is called an acidic workup, where you add in a little bit of dilute acid at the end. All right, but this is lithium aluminum hydride. And our weak oxidizer is sodium borohydride. All right. Our oxidation reactions, we're going to leave these like as a mystery to us in terms of how our mechanisms go down. We're going to note, and we'll do this here in a second, but let's just put the little star next to it because this is another reaction that we're going to have a mechanism for. All right, we'll take a look at that here in a second, but let's first address this strong versus weak categorization here. All right. Similar to what we saw with strong and weak oxidizers, these things have different reduction potentials. Okay. It turns out that our weak oxidizer is too weak to oxidize that carboxylic acid. It can only oxidize an aldehyde into a primary alcohol. If we wanted to oxidize a carboxylic acid into a primary, we would have to use our strong oxidizer. All right, now, if you wanted to, you could use your strong oxidizer on an aldehyde, and that would take you to the same place. I'm sorry, strong reducer. That would take you to the same place, all right? But if you're trying to reduce a carboxylic acid, you have to use our strong reducing agent. Okay, and then when we're talking about ketones and secondary alcohols, you could use either. Either one would do the same thing. Cool. All right, so just kind of a little bit of a cheat sheet here. Primary alcohols can be oxidized to aldehydes, which can be oxidized to carboxylic acids. Secondary alcohols can be oxidized to ketones. Tertiary alcohols cannot be oxidized. All right. If you used a strong oxidizer, you would create a carboxylic acid from either your primary alcohol or aldehyde. If you wanted to convert a primary alcohol into an aldehyde, you need to use a weak oxidizer. Likewise, if you were trying to reduce, if you were starting with a carboxylic acid, you'd have to use a strong reducer. If you were starting out with an aldehyde, you could use either your strong or your weak reducer to do it. All right, and then either one does the same thing when we're talking about oxidation of secondary alcohols or reduction of ketones. All right, only that one oxidation reduction step. Okay, so I said we were going to look at our mechanism for these reduction reactions. It's the same mechanism regardless of which one you look at here. But what do these both have in common? A lithium aluminum hydride, sodium borohydride. What's in the name that's the same? Hydride. Okay, and when you hear hydride, you want to think that means that we have a nucleophilic hydrogen. All right, and I know everybody, I just like collectively heard everybody's organic chemistry brain explode, and you're like, what? Hydrogen's playing the role of a nucleophile? That never happens, right? No, hydrogen's almost always an electrophile. We just talked about how acids have that electrophilic site as that hydrogen atom. So these are what makes these compounds special, is these hydrides are special because we're gonna see hydrogen playing the role of a nucleophile. All right, so let's do our reduction reaction mechanism. right, so first of all, the sodium, what do we think the sodium's doing for us in this reaction here? Just being a cation, just being a counter ion, right? So the borohydride's the interesting part. Likewise, lithium's just a counter ion. It's the aluminum hydride that's the interesting part here, all right? In order to do our mechanisms correctly, we are going to have to draw out our Lewis structure for these molecules. So let's just take our aluminum hydride. Again, since lithium is a positively charged cation, that means that this thing all has a negative charge associated with it. Same thing with our sodium borohydride. If we take away that positively charged sodium ion, our borohydride ion has that negative charge. All right, and if we're going to do our Lewis structure, all we're going to do is draw our central atom here with its 4 bonds. And note that that central atom has a negative charge. All right, likewise, same thing over here, except I would replace my lithium with a boron. Okay, so let's take one of these. They're going to be basically the exact same, so I'm just going to pick one. All right, and let's react this. With a ketone. Boom. All right, so this we're going to react with that aluminum hydride here. And I told you that that hydride is going to play the role of the nucleophile in this reaction. So that means that this ketone is going to be the electrophile. What's the electrophilic site on a ketone? Where is this atom that lacks electron density in this ketone? That carbonyl carbon, all right? So one phrase, and we like close out this course by talking about all these carbonyl containing compounds. And one thing you're going to hear me say over and over and over again is the electrophilic carbonyl carbon. We want that phrase kind of jammed in our mind here. Okay, so I know my nucleophile is going to attack my electrophile. We got to be careful though. What's wrong with this electron pushing arrow? So it would break the octet, and so how am I going to make sure not to break the octet rule? Pi bond pair of electrons has to jump up here. But there's something still wrong with that first arrow. All right, it would be kind of like a minor point deduction here. It's not the biggest sin in the world. But specifically looking at the base of that arrow, what's incorrect? It's not at a pair of electrons. And importantly, hydrogen doesn't have lone pairs, right? Typically, we start these things at lone pairs, and that lone pair is what's reaching out. But the bottom line, the big rule is that they have to start at a pair of electrons. So what's the pair of electrons that is going to be accepted by that carbonyl carbon? All right, I have to draw the base of my arrow at that aluminum hydrogen bond. That's my pair of electrons that is going to be doing the attacking here. All right, so again, not the biggest sin in the world, but it is technically breaking our rules for electron pushing arrows. So if you want full credit on your exam, you're going to make sure to start the arrow at that bond. All right, now this is going to kick off that ALH3, never to be seen again. It's not going to be important here. All right. And importantly, what we've created is this new carbon-hydrogen bond. All right, so over on the other side, our oxygen has this net negative charge. All right, and you're sort of stuck here. This molecule is stuck as this alkoxide ion here until you do the second step where you add in that dilute acid. And the whole purpose of that second step is just to plug up or protonate that alkoxide ion. Right? So we add a little dilute acid in there just to protonate our oxygen, giving us this alcohol product. All right. Now, I'm drawing in that I could have left that hydrogen implied, but I want to make kind of a point about this. One thing that I see people do all the time when I'm asking for the reaction mechanism of this reaction, where am I? Is they know that they need to create an alcohol, so they say the oxygen grabs that hydrogen. That's our reaction here. This is not how this reaction went down. All right, the whole point of that hydride was that it was a nucleophilic hydrogen. So importantly, where did that hydrogen go in my lithium aluminum hydride? That's what attacked that carbonyl carbon. Where did the hydrogen on my oxygen, on my hydroxyl group come from? That acid. All right, so important difference here to note, or rather important thing to keep straight in our mechanism. All right, we've added two new hydrogen bonds, a carbon hydrogen and an oxygen hydrogen bond, but they came from very, very different sources, right? My carbon hydrogen bond came from my hydride. My oxygen hydrogen bond came from that dilute acid. Cool. All right, one more that we're going to introduce here, and this is going to be important. We're going to see this reaction over and over again, what's called a Grignard reaction. All right, one of the reasons why this Grignard reaction is going to be so notable, first of all, it just works really well. Okay, it's kind of magic how it works. So, I mean, we'll talk about it here in a second, but it works really well. There's not a lot of restrictions on like the molecules that you can use in this reaction. It's very robust. You can use it with primary carbons, secondary carbons, sp2, sp3, whatever, right? So it's just got a lot of flexibility to it that makes these Grignard reactions great. They get high yields, all right? It's also notable because it's going to create a new carbon-carbon bond. We don't have a ton of ways of creating carbon-carbon bonds, so we always want to kind of just make special note of those reactions that fall into that category. Okay, so a Grignard reaction uses what we call a Grignard reagent, which is one of those organometallic compounds. What do we think the organo in organometallic means? It's organic, and what about metallic?
Metal.
There's a metal in there, all right? So this is one of these weird compounds that has one of these things we almost never talk about in the course, a metal in there. And this is why I say it's magic. So basically we take an alkyl bromide, and we'll do this in the lab in 2 weeks, all right? You toss in some magnesium shavings, and that magnesium is going to insert itself between the carbon and the bromine. All right, this MgBr is our Grignard reagent. So this is how we make our Grignard reagent, and then we take this thing and react it with other stuff. All right. right, so Grignard reagents here. If we look carefully, let's think about what role this Grignard is going to be playing in our chemical reaction. All right. Well, what we want to note is in this carbon-magnesium bond here, which one of those atoms is more electronegative? Carbon. So carbon, when we're talking in the context of our nonmetals, is not very electronegative, right? It's less electronegative than everybody else we talk about in organic chemistry. But now, since we're comparing it to magnesium, all the way on the opposite side of the periodic table, a metal, carbon as a nonmetal is much more electronegative than our magnesium, which means that in this molecule here, all that electron density is sitting on that carbon atom, and not very much electron density on our magnesium. So our Grignard reagents here are playing the roles of nucleophiles. Specifically, our nucleophilic site is a carbon atom. All right, so Grignard reagents, why they're special is because they have these nucleophilic carbons. All right, again, not an atom we see playing the role of a nucleophile very often, but because it's in this special carbon-magnesium bond, carbon-metal bond, it's the more electronegative atom, and it's pulling all that electron density away from that magnesium. All right, so now let's take this and do a reaction here. We're going to see Grignards react with a whole bunch of different electrophiles. The ones that we're going to be concerned about for this particular chapter are aldehydes and ketones. Okay, so let's take our Grignard reagent. That MgBr molecule that we created. And we're going to react it with this aldehyde here. All right. Our Grignard, we said plays the role of the nucleophile, so our aldehyde is going to play the role of the electrophile, and specifically, what's the electrophilic site on that aldehyde? That carbonyl carbon, right? Same game we were just playing. Okay, I have my nucleophilic carbon reacting with my electrophilic carbon. All right, our nucleophile is going to attack our electrophile and kick that pair of electrons up. But real quick, what's wrong with this electron pushing arrow, that first one? It's on an atom, not on a pair of electrons. All right, so similar to what we just saw before, we have to be careful about our electron pushing arrows for these reactions. The pair of electrons doing the attacking are the ones that live in that carbon-magnesium bond. All right, so our MgBr is going to go flying off into space, never to be seen again, not going to be involved in the rest of this reaction at all. Okay, but importantly, now I've created a new carbon-carbon bond. So I've connected those 3 carbons from my Grignard. I have this new carbon-carbon bond. What must live on the other side is that electrophilic carbon. Right? So we've created a new carbon-carbon bond between our nucleophilic carbon and our electrophilic carbonyl carbon, which means we got to be good and keep the rest of those carbons on there. So I had these 3, 1, 2, 3 from my nucleophile. I'm going to need 1, 2, 3 from my electrophile. All right, and then what else am I missing here? My oxygen is still bonded, but now it's just a single bond, and it's accepted that pair of electrons, so we have another alkoxide intermediate here. Okay, these Grignard reactions, just like our reduction reactions, you're stuck here until you do this follow-up step where you add in dilute acid. They call an acidic workup. And that acid is just there to protonate that oxygen, creating your alcohol product. All right, but importantly, we've created an alcohol that has extra carbons on there. All right, so this is our Grignard reaction mechanism here. Okay, and just to summarize, if I had this aldehyde, all right, how we would sort of write out these reagents is that first step was me adding in that Grignard, and then I had to do a second step that was that acidic workup. And what I created was now this 6-carbon alcohol. All right, where importantly, I connected my 3 carbons from my Grignard, specifically at that nucleophilic carbon, to my 3 carbons from my aldehyde, specifically at that electrophilic carbonyl carbon. Okay. So these reactions are, the mechanism is really not too bad. That's that 2-step mechanism there. The key thing, the hard part about these reactions is going to be you create a new carbon-carbon bond, so your product's always bigger and uglier than what you started with, all right? That's also why making sure you count your carbons is going to be really important. All right, so let's just practice this. Now we'll take a ketone. I'm going to add in just an ethyl Grignard. We'll do something a little more complex. What's up? This is a mechanism that you need to know, yep. You don't have to do it here, right? So you can get the product simply, but yes, if I ask you for a mechanism, you should be able to give it to me. All right, so how am I going to do this here? First thing I'm going to do is identify my electrophilic site and my nucleophilic site, because those are the two atoms that I need to link together in this molecule, right, when I create my product. So you could start with either one, but basically we're going to start by redrawing. In this case, I'll pick my electrophile. So I've got these 3 carbons, so I'm going to start by redrawing those 3 carbons. Boom, boom, boom. And note that here is my electrophilic site. And in this reaction, I know I've created a new bond between that electrophilic site. So what must live on the other side of that bond? That nucleophilic carbon. And I'm just going to make sure to draw in all those, in this case, 2 carbons from my nucleophile. I just can't forget that I also have that oxygen creating that alcohol group still bonded to what was formerly my carbonyl carbon. All right, now this one's a little bit more of a pain. So again, we're going to trust the process. We're going to identify our electrophile, identify our nucleophile, and I'm going to start by redrawing all of these carbons from my electrophile. All right, so I should have a total of 1, 2, 3, 4, 5 carbons with that little fork in there. All right, so here are my 5 carbons from my electrophile. And again, I'm noting specifically what my electrophilic site is. All right, so then if I know that this reaction created a new bond between that electrophilic carbon and my nucleophilic carbon over here in my Grignard. All right, so now I'm going to draw the remaining carbons attached to that nucleophilic carbon. I have 1, 2, 3, total of 4, so that's 1, 2, 3, 4. And then I need that last one coming off of that 3rd carbon. Boom. All right, and then lastly, my oxygen still bonded to that what was formerly carbonyl carbon. That's where my alcohol group should go. Okay, so this is my product here of this Grignard reaction. Cool. And we'll sort of pick up with this same thing next time, next class period, and just do some more practice with Grignards. All right. They, not too bad. Got to trust the process, but you do get these big, ugly products out at the end, so keeping track of who's who is very important. Cool. All right.